quantum communication system for image transmission over electron channels. Under this topic, we are planning to discuss with what is the quantum communication, why we are using quantum communication, and different methods of quantum encodings, and why multi-qubit encoding is most important for the quantum communication. Let's move to the introduction. First, what is quantum communication? Quantum communication is a way of transmitting information using quantum mechanical properties. Unlike in classical communication, which uses classically to transmit information, quantum communication uses quantum bits or qubit to transmit information. Due to the mysterious behavior of the quantum world, these qubits can exist in multiple states at the same time until we measure it. We are calling it to quantum superposition principle. Quantum superposition means ability to transmit information higher than one state using due to the behavior of the quantum mechanics. In the quantum communication systems, we can use qubit to represent the information, like same as the classical communication. We are using qubit 0 and the qubit 1. This is the qubit 0 representation, and we are calling it to ket 0, that is the ket vector notation, and also we can represent that ket 0 as a column matrix 1 0. Also we can use ket 1 to represent the qubit 1, and we can represent it as a column matrix 0 1. If we apply quantum superposition into this qubit state, we can get the superposition state. To apply the quantum superposition, we are using Hadamard gate. This is the Hadamard gate. It is a 2 by 2 matrix. If we apply Hadamard gate into ket 0, we can get the result 1 over square root 2 ket 0 plus 1 over square root 2 ket 1. We are calling it to plus superposition state. If we apply Hadamard gate into ket 1, we can get the results 1 over square root 2 ket 0 minus 1 over square root 2 ket 1. We are calling it to minus superposition state. This is the single qubit encoding, but it is different from our case. We are using multi-qubit encoding. I will explain what is multi-qubit encoding in next slide. First, I need to discuss why quantum communication for image transmission. Due to the behavior of the quantum mechanics, we can get several advantages for the image transmission. Some of them are high noise resilience, high reliability, efficient use of bandwidth, low latency, and fast and resource efficient media transmission properties of the quantum communication. What is multi-qubit encoding? Multi-qubit encoding is a quantum encoding technique that uses multiple qubits to represent the information. Using this multi-qubit encoding, we can get a lot of advantages, especially high noise resilience. Why multi-qubit encoding for image transmission? Because as I mentioned earlier, we can get high noise resilience for the image transmission. It enhances the system robustness by distributing information across quantum state in a high-dimensional Hilbert state. It also improves error resilience and noise mitigation, and also it supports advanced encoding schemes and better scalability, enabling reliable transmission over longer distances. The main objective of this research are improve the quality and robustness of the image transmission under noise, replacing single qubit encoding with multi-qubit encoding, and assess the impact of computational complexity with the qubit encoding size. The key innovation of this study are use a novel advanced quantum encoding method for the quantum communication, propose a multi-qubit quantum communication system for image transmission, and introduce an adaptive multi-qubit quantum communication system for image transmission that dynamically adjusts the qubit encoding size based on the channel conditions.
I'd like to present the proposed methodology for this framework. So what we do is initially we get the original image, which can be like an uncompressed image, and then we have a source encoder. The job of the source encoder is to compress the image using different image models. Here we use JPEG and HEIF, and then we have channel encoder. This is a classical channel encoder. We can use any other channel encoding techniques like LDPC, polar codes, or whatever it is. And then after channel encoding, we have the multi-qubit encoder, which is the core of this work. So what we do here is like we convert this classical bit to qubit mapping here, and then we select the qubit size depending on the channel constraints, basically the bandwidth of the channel. And here we have a feedback loop to control the source coding and the channel coding, so source coding and the qubit selection to make it the same channel bandwidth with respect to the quantum channel. For example, if we have a single qubit system, and let's assume that we have a bit rate of x, and if we increase this to 8 qubit, channel bandwidth goes to be increased by 8 times. So using the feedback channel, we compress the source information 8 times more compared to the single qubit situation to make it the same channel bandwidth. After that, we will convert this into quantum symbols using the Hadamard gate, and then translate to the quantum channel. And here we have another feedback loop to select adaptive selection of the qubit based on the channel condition. For example, the channel is burst, so according to that, we will select the qubit orientation. So that's happening at the encoder and the channel. So at the decoder, multi-qubit decoder, we basically do the reverse operation. We have a reverse Hadamard gate to map them into the qubit at the decoder. So once we enter the qubit, we have a classical qubit to classical mapping. So qubit to classical mapping to get the conventional bits. And after that, we have a channel decoder to convert them back to the source information, and finally we have the source decoder to regenerate the decoded information. So HEIF and JPEG are being used here, depending on the type of the source encoder we use as the decoder. And finally we can compare the reconstructed image and the original image using PSNR and SSIM and the mapping. So that's basically the proposed methodology with the maximum of the game from original image to the reconstructed image.
Baseline reconstruction, maybe 11 dB something on the baseline.
Quantum Fourier transform.
Yeah, that's a quantum version. And so you use the diffusion model was trained on the original dataset, right?
Yes.
And then you put the
No, original dataset, but for Q noise.
Yes.
So the UNet was basically trained from the noisy dataset.
That's what I think they have done, right?
To encode these quantum state into the quantum superposition, we can use the Hadamard gate. For the single qubit system, we use the 2x2 Hadamard gate, but for the 2 qubit system, we need to again create the 4x4 Hadamard gate. That means we have 4x1 column matrix in the 2 qubit case. Therefore, to create the 2 qubit encoding system, we need to get the tensor product of 2 individual single qubit Hadamard gates, and we can create the 4x4 matrix like this. If we apply this 4x4 Hadamard gate into the constructed 2 qubit quantum state, we can get the superposition state like this, and this quantum state can travel through the quantum channel. In the quantum channel, we use 5 canonical noise types to represent the quantum noise behavior. We use bit noise, phase shift noise, depolarization noise, amplitude damping noise, and finally phase damping noise.
So I will be discussing multi-qubit decoding. The corresponding Hadamard gate again can be used to extract the quantum states from the qubit superposition states, because the inverse of the Hadamard gate is the Hadamard gate itself. When a quantum superposition state is received in the absence of noise, the original classical information can be accurately extracted. Okay. In a noisy situation, similarly, we can apply the Hadamard gate to the noisy superposition states, allowing the corresponding quantum state to be mapped to the nearest predefined quantum state. Afterwards, the recovered quantum states can be correctly mapped. So I will be discussing multi-qubit decoding. The corresponding Hadamard gate again can be used to extract the quantum states from the qubit superposition states, because the inverse of the Hadamard gate is the Hadamard gate itself. When a quantum superposition state is received in the absence of noise, the original classical information can be accurately extracted. Okay. In a noisy situation, similarly, we can apply the Hadamard gate to the noisy superposition states, allowing the corresponding quantum state to be mapped to the nearest predefined quantum state. Afterwards, the recovered quantum states can be correctly mapped to the corresponding qubits using Euclidean distance, as these states lie in the computational basis and are directly related to the classical data, from which the classical bits can be extracted. So these were the results we got from JPEG. And these are the results from HEIF image transmission.
Yeah. Okay.
So Increasing the number of qubits used in encoding results in significant improvements in both error distance and image quality when compared to single-qubit encoding. The system supports an arbitrary number of qubits. This study utilizes qubit encoding size from 1 to 8, ensuring constant bandwidth usage across all configurations. The system achieves its best performance with 8-qubit encoding in high-noise environments. However, this improvement increases complexity and resource usage. With channel coding, this setup delivers up to 15 decibels and 17 decibels SNR gains for JPEG and HEIF images, respectively compared to single-qubit encoding. These improvements result from the combined benefits of multi-qubit encoding